Okay, let me just check. So hi everyone. Many thanks, Eric, for giving the overview, really useful overview, and for inviting me in the first place to make this contribution. Thank you to the ICE Core Young Scientists for having me and and organizing. So diffusion-advection of climate signals recorded by ice vein ionic impurities. This talk concerns the records of soluble ions, examples which you can see here. Some of the opening here might overlap with what Eric told you about. And I won't say too much about the paleoclimatic interpretation because I think most folks here know way more about that than me. But I will talk about processes that potentially threaten the integrity of these records. Now, these records are quite typical in that they illustrate the very short, diverse variations at decimeter, subdecimeter scales, representing various paleoclimatic processes and changes. And if I'm right, I think some of the very sharp signals like volcanic spikes are used for synchronizing the age scales of different cores, and if not, at least to check their dating across different cores. Now, if any distortion to the signal position or form happens, then our interpretation may be compromised, and that's my focus here. So consider only those changes or signals carried by single ions to keep the story simple, and only those ions dissolved in the liquid veins under the Fern transition. So we won't worry about what happens in the Fern. And yes, the story is that 20 years ago, Rambo had this theory that these signals would have moved relative to the ice when there's a temperature gradient, which disrupts the dating. And my new analysis shows something different, that the signals migrate, but they diffuse rapidly. In fact, so rapidly that they don't survive into deeper ice to be able to show the said displacement. I think especially establishing this finding will get us most of the way in my talk here, but I'll certainly cover the numerous implications that follow from them and where I think modeling ought to go next. So here are the water veins, a 3D network of liquid located at the triple junctions of between crystals, kept liquid by the high impurity concentration in it. It's thought that grain boundary motion and recrystallization processes can move impurities from within crystals towards grain boundaries and then to the veins, and hence the concentration there. This vein radius RV will be important on the next slide. I'll come back to this. If the veins occupy a volume fraction of the ice of phi, and this is like a porosity, and then if the vein water in these strands has impurity concentration of C, then basically the bulk ionic concentration of the species that you measure for the ice is just a product. And we're going to, this is what the Rampo theory models, and that's what we're going to model here. But remember, this is just going to be the vein contribution to of impurities towards a major ion record, which may include impurity contributions from grain boundaries and within crystals as well, including at these micro-inclusion sites. We're not going to model this. I need to learn more, able to tackle the modeling of these and the coupling, but we'll come back to involve them in the discussion at the end. So as Eric outlined, Rampo's theory posits that these vein signals move relative to the ice towards higher temperature. These are cartoons from the paper, and the idea is that as ice descends towards the bed, compressing under vertical compressive strain, the chemical signals in it displace a little bit from the ice, just a little bit. We talk about half a meter, something like that in deep ice. Now they call the mechanism enormous diffusion, but actually is an advection. The signals migrate but don't actually diffuse, as you can see in the cartoon, even though the underlying cause is chemical diffusion in the veins down this gradient. and this is a gradient of the vein impurity concentration, whereas the signals are sitting on the bulk variable CB, and that's a really interesting thing about their theory. And they calculated for the grip site, as Eric also outlined, that migration velocities are on the order of several hundreds of millimeters per year. This is for the deeper part of the core, deeper third, where temperature increases rapidly towards the bed, giving us there in that section displacements reaching a meter or so. So yes, the concern is potentially large age offsets to climatic signals recorded by ions at depth, which may disrupt their alignment from other proxies and the dating. Some folks think that migration doesn't happen though, either because the veins are blocked or disconnected in some way. That's going to kill this diffusion in the veins, or that the records we measure are made up mostly by crystal and grain boundary impurities, which don't migrate by this mechanism. We just talk about vein signals. So how does the mechanism actually work? If you have a piece of ice at some temperature, with somewhere down the core T, and the ice has a mean grain size dg, approximately shown here, and the bulk concentration there is CB, then these equations describe the conditions in the veins. We can easily rewrite the porosity by using the other dimensions, the mean grain size, vein radius, and so on. And then there's a second equation, which is the liquidus relation, telling us melting point depression due to solid. So this gamma is just the liquidus slope. It's particular to the iron species being considered as binary system with water. And in their theory, this liquidus relation translates, as you can see over here, the rising temperature towards the bed, especially deep in the ice column, to a decreasing, there's a minus sign here, decreasing impurity concentration of veins, which drives that downward diffusion of chemistry in the vein network. When you zoom in there, the gradient is very shallow, very slow diffusion here of chemistry, but that interacts with the porosity expression of a signal, of a bulk signal, to move the signal. And the way it works is that on the upper side of the signal, the porosity increases with depth. And so the downward chemical flux increases with depth, and that draws down the signal. Whereas on the leading edge, the opposite happens. And this is really neat kinematic way. It's like a carpet warp. You push on the rear and you lift the front, the carpet warp moves along, and it turns diffusion into advection. So when we formulate all these ingredients into a continuum model, you get this differential equation, which is their model. Obviously, at ice core sites, the signal is going to be narrowed under compression, but then we get this additional migration of the signal against the ice. And I've highlighted the migration velocity in blue here. It's faster when warmer. Now, they actually realized in their theory an extra melting point depression coming from this term because of the curvature of the ice-water interface. And so this vein radius RV is involved. This is the Gibbs-Thompson effect. And gamma here is a interfacial energy, is a non-constant. But they didn't actually include this in their calculations. And when I did, I found that the signal behavior is different, and the implications for the how we interpret observations becomes radically different. But what happens now is that this second equation is no longer a straight line. If you're interested in mathematics, this is basically a solution telling us conditions in veins at a certain place. But now, because equation 2 isn't a vertical line, it's tilted. When you get a signal in the bulk concentration, you move across it, there's a little perturbation on the vein impurity concentration that causes diffusion. Yes, again, it's very shallow, but that actually diffuses the main signal. So that's summarized here. There is this Gibbs-Thompson effect, which perturbs the local vein chemical concentration, which in turn diffuses the bulk signal. Yeah, and now our model includes this extra diffusion term, which is non-linear. It's going to apply to to any ionic species, dissolved ionic species that obeys equation 2. Yeah, as if this is not complicated enough, there's actually another diffusion coming from the fact that in polycrystalline ice, recrystallization is happening all the time. Grain boundaries moving continually, even if the grain size is constant, and the associated vein motion in 3D in all directions causes an advection. It's like a scattering. It's almost like kinetic theory of gases. And when you have a gradient in bulk concentration, you get a net diffusion coming from it. At a rate related to grain growth rate. And I call this the residual diffusion because even if you block the veins, so chemistry can't flow along the veins, this is going to happen. You get residual diffusion from grain boundary motion, which doesn't cease. So what we do now is to solve this equation in several experiments with just taking sulfate as our impurity, where we inject test signals just under the firm transition and then see what happens to them in position and shape. The Z prime here is the coordinate following the ice, if you're interested. Basically, whenever Z prime is positive, the signal is shifted from the ice. So I'm going to show you a few experiments turning on and off the Gibbs-Thomson term to see how that impacts Rampel's theory. Some experiments will have different initial peak widths, amplitudes, and then in some we switch off the molecular diffusivity. We reduce it to mimic blockage of the vein system or disconnection. Here's the first experiment along the top, including all processes. I call this control run. We inject an 8 centimeter wide signal, which is actually a bit wider than that. 8 centimeters refers to the characteristic width of the Gaussian. We inject that 100 meters down where the H is about half a kiloyear. We're at the grip site here. So we see rapid decay of signal amplitude. We've just passed 20,000 years, about 2/3 of the way down, and the signal has been eliminated. Let me play this again. The signal has hardly a chance to migrate under Rampel's mechanism because it diffuses so quickly. So we already see in this test that the signal really struggles to displace any migration because of the strong diffusion coming from this perturbation in C. This is the chemical concentration of veins, which mirrors the signal and drives diffusion of the signal. When we switch off the Gibbs-Thomson, this is approaching Rampel's theory now. The signal amplitude survives longer. We're now able to see the migration. The signal still decays though, because of residual diffusion, which we didn't switch off. And this is coming from grain boundary motion. So let me play this through. This dial up here applies to both simulations. Migration rates are high towards the bottom of the grip core because of the high temperature gradient there. But essentially halfway down the column, we've lost motor signal, the integrity is lost. Here is an equivalent experiment of dome C, same injection really. Again, 2 experiments. Rapid decay of amplitude, signal amplitude again. At apica, there's a bit of more of the temperature gradient, even in shallow ice, so we see more visibly the migration. We're about halfway down now, and most of the signal content is again gone. And remember, I'm just modeling the vein impurity contributions, not the impurities in grain boundaries or the lattice. When we switch off Gibbs-Thomson, really the same behavior. We have prolonged signal amplitude survival. A bit more of the signals preserved for longer, but residual diffusion becomes important towards the bed in warm ice. Perfectly preserved signals just move along, narrowing with no change in amplitude. Yeah, so here are the histories. Sorry, complicated diagram here. But these are now histories of the signal amplitude at grip, amplitude on the left, signal width as we track it in time and depth. In the middle, this is measured as a full width at half maximum. and the associated duration of the peak in time, in the time domain, the age span. The black curves show the very rapid decay of signal. We've lost the signal basically by 20,000 years, about two-thirds way down. The orange curve shows us prolonged survival of the signal to about 2,500 meters. But it doesn't survive the residual diffusion down here. This is with the Gibbs-Thomson effect switched off, which is not physical because it's really there. This really just shows the difference between Rampo's theory and the theory where we have old processes. We try injecting narrower peaks and wider peaks, as well as wide as 32 centimeters under the firm, very wide. And such wide peak still survives only marginally longer. It gets killed at about 2 kilometers down when the age is only 30,000 years at grip. I won't talk too much about the width evolution, but it's essentially controlled by the competition between diffusion and compression. The important plots are to the left. So to keep signals for longer, we need to do something more drastic. One way to get signals down here to the bottom third of the core is to block the veins. And here we do this by suppressing D by 3 factors, as shown by blue curves. 1,000-fold blockage of the veins, pretty much block veins, gets the signal down to an 8 centimeter initial signal down to 2,600 meters. So the long residence time of the ice there still kills the signal through Gibbs-Thomson and residual diffusion at the high temperatures near the bed. So bottom line is that it's very hard for signals to get down here. Perfect signals would follow these trajectories. We're not even near that. Oh, yes, I should also show you the simulated displacements of the peak signals, signal peaks from the ice, and the associated age offsets. So in black here again is the control run. We can get very large age offsets in deep part of the grip core, more than 1,000 years. I don't bother to show you this part of the curve here because the signals don't get there in terms of amplitude. They migrate, but their amplitudes don't survive, as you can recall from the last slide. Now, when we do prolong signal survival by blocking the veins, what we do is that we decrease D, but we also minimize signal migration. So when we allow signals to get to deeper ice to survive in amplitude, they don't migrate, as you can see from these blue labels. In fact, 1,000-fold label, there's a curve here that is basically vertical. So yeah, it's a catch-22 situation for the Rampo theory. Signals, when they migrate, because of an open vein system, their amplitudes decay before they can show the migration. If we slow the diffusion, we also slow the migration, so signals don't migrate anymore. The results for EDC is similar. These are just the same set of experiments run there. These H spans out here, these are the widths of signals in the time domain, could potentially define the resolution of paleoclimatic signals we can get from the EDC core at depth. I think Eric alluded to this idea, and how well can we actually obtain information down there in terms of time resolution. And these runs could actually tell us a bit about that, except that signals don't survive in amplitude there, so we can't use these. If signals get there because of blocked veins, then we might use the blue curves. But as you can see, the age resolution becomes much better, even blocked veins. For completeness, I show the Epica signal displacements and age offsets as well. Conclusions are identical. Short scale signals can't survive in the deep ice where their displacements matter paleoclimatically. On the other hand, if they do get there because the veins are blocked, they would hardly have migrated. So these are the results really. Rampo's mechanism operates if the veins are connected, except that there is a strong diffusion that eradicates the amplitude before they can reach deep ice to show that age offset. If they do get there, because the veins are blocked, they haven't migrated. If they migrated, they wouldn't have survived the diffusion to get there in the first place. Well, we've only modeled the vein signals. The actual records include contributions from grain boundaries and crystal matrices, which don't migrate by Rampo's mechanism. Some of these impurities could feed into the veins, though, and refresh the vein signals. If you see any vein signals that are short, well-defined, obtained from such sources, they wouldn't have migrated either. If they're there, if they survive the diffusion, they wouldn't have migrated. If they migrate, they would wane away very quickly. So the conclusions, I think, is that the deep peaks and spikes that you see on the records depth haven't displaced. Not for us to worry about displacement and major offsets. Basically, individual signals coming from the veins, because they're there, they must be surviving in a blocked vein system, so they haven't migrated, or those signals actually derive from grain boundaries or the crystal matrix, which don't experience Rampo's migration. And I think, therefore, the dating concern goes away. We can stop worrying about Rampo's theory from the physical basis of Rampo's theory, with more physics included. There may be an issue with signal content preservation. The major iron records are made up from these three impurity contributions, as I mentioned, from the veins, component 1, from grain boundaries here, and from crystal matrices. And for individual climate signals, initially consisting of all three components, the vein part, most of it or all of it might have gone down core. And so we might have to think of our iron records as made up of components 2 and 3, grain boundary and matrix impurities, and whatever that's left over in the veins that hasn't diffused into the background because of Gibbs-Thomson diffusion. This is just a cartoon on the right, is not real. It's a speculation of how badly, how much signals have been lost, might have been lost to the veins in a bad case scenario. I don't know how much has been lost. If the veins are blocked, then much less. Or if climatic signals on entry to the top part of the core quickly segregate to grain boundaries or crystal matrix away from the veins, then not much can be lost. But I really don't know the partitioning. Yes, even if the veins are blocked, residual diffusion will damp signals, though, at depth where the ice is warm. And in fact, the residual diffusion, because it involves grain boundary motion, will also damp grain boundary impurity signals, component 2 there. And I think this may be interesting. It may be interesting to consider whether it's an issue for the planned Little Dome Sea project, where I think the ice is meant to have a very long residence time there, maybe approaching a million year, below 2,500 meters, or is it below 2,000 meters? The last 500 meters or so, very long residence time. In terms of obtaining robust interpretations from these records, I think we need to start trying to partition these records into the three impurity components and understand how they interact and evolve physically. But we know very little about those underlying physics. I mentioned earlier that impurities could move between different locations. There may be other directions as well. So the bottom conclusion here is that I think we should try and disentangle these components, understand the physics to refine and extend our interpretation of the records. One more thing I want to show you, I've just squeezed this in. The model actually shows an additional interesting result when short-scale grain size fluctuations are there in the core. It turns out that when you use those fluctuations to drive the model, new signals spontaneously appear. So on the right are a couple of simulations. Here is grain size here. Uniform grains, a piece of ice, uniform grain size, except for a decimeter or so, there's a much finer grain size. In this experiment, we just let that signal descend towards the bed uncompressed. In this, we let it compress with layer thinning. And then we couple this to the equation that I showed you. what we find is that these grain size fluctuations drive the spontaneous evolution of signals locked to them, not migrating. But these signals are non-climatic in the sense that they didn't come directly from the deposition. So one issue may be that recrystallization processes can generate short grain size fluctuations in the ice cores. We know there are lots of fluctuations in grain size. And then these spurious non-climatic signals could further corrupt our records. This is just a theory. We need to do more with this, comparing observations, maybe with grain size profiles. So I just want to wrap up here with this final slide with a few areas where I think we need much more physical understanding in order to tackle this inverse problem of reading the records for past inputs accurately. We need to disentangle the impurities, components, and the interactions. We need to understand impurity transport between different locations, conversions between liquid and solid impurities, and also in different part of the system. I'm sure that chemical reactions and associations will get in the way and make this very complex. I think there is very strong coupling between impurity processes and recrystallization processes that control grain size and fabric evolution. Grain boundaries could sweep material from interiors towards the grain boundaries themselves and transport them. Ionic impurities could impede grain boundary motion. And then I just showed you simulations where grain size fluctuations could induce new signals in the vein component of the record. And then finally, we need to understand controls behind the connectivity of the vein network as well. The processes here could be very dynamic in regulating which part of the vein system is connected or not. And I think the model I showed you earlier was just the tip of the iceberg in this subject. And I'll stop there.
Thank you, Alexis, Felix. Well, I think the implications you showed of this study are extremely interesting. And yeah, I think we have time for a couple of questions. I see that we have one from Christoph Buser. Are you able to see it, or should I read it for you?
Absolutely. Can everybody hear me?
Oh, yes.
Yeah,
sure.
I was, thanks, Felix. Very, very interesting. I was just wondering, in all of your equations, it appeared that you treat the vein as a single, like there's a single 1D vein going all the way from the top to the bottom. But in reality, I guess that there's some tortuosity to the vein network, and also the porosity, as you defined it, probably decreases with depth as the crystals get bigger. And there's 3D branching. So some of those veins are going to be perpendicular to the gradients, right? And they will not really contribute to that diffusion as much. So maybe I missed it. Did you include that, and or is it important?
Thanks, Crystal, for that question. It's the veins in this theory are 3-dimensional in the sense that the only important variable really is the porosity. Yeah. So what Rempel did was that they fiddled with the diffusivity that I showed you. I think they reduced it by a factor of 3 in order to capture the different directions of chemical diffusion in the vein system. So if it really is one single vein, then the normal value of the diffusivity of molecules in water would be used. And what they did was to make use a smaller value for that, about a third, to represent that. But the vein geometry, system geometry, doesn't matter in the sense that the single important continuum variable is the porosity, and is lumping together all the vein volumes. Yeah, does that help?
Yes, absolutely. So yeah, it is included just implicitly into the diffusivity. Yeah, so it's sort of like a tortuosity term, right? So it's the diffusivity in a free vein divided by the tortuosity, which you set to 3. So that makes sense to me. Thanks.
Yeah, I think you're right that one could potentially model the grain scale chemical transport. Yeah, chemical transport in the vein system at the grain scale. This is not done in that model because it's continuum in the sense that everything is averaged above the grain scale. Yeah, well above the grain scale. Thanks. Sorry for eating into your part of the talk here, Giovanni. I think I went slightly over time.
Yeah, I think if there are no more questions, then we can move on to Giovanni.
Hubertus has a question. So
Yeah, I have
Hubertus,
a question for Felix.
Okay.
Can you hear me?
Yes.
Okay.
Yes, Curtis, hi.
One of the, and you alluded to it at the end, one of the important things is how much of the impurities are really in the veins, how much are in the bulk crystal, how much are in the grain boundaries. And what is your picture actually, what determines the amount of the impurities in the veins? Are they there to start with during, let's say, snowflake formation, or are they actually resupplied during the grain boundary migration in the ice?
Thanks for asking this, Hubertus. I'm quite ignorant of the real process there, but I've read and therefore I take as a kind of my working hypothesis at the moment that that in the fern there's already some segregation process going on that determines how much of a certain type of impurity ends up within the matrix at grain boundaries and the veins, and then there's around in the literature there's been a concept that as grain boundaries move, they could sweep up impurities. They may even leave behind impurities, but there's an idea that they can sweep up impurities and gather them, and then because the veins are sitting at the junctions between grain boundaries, material will end up there. But whether what controls whether the overall transport is towards the vein as away from them, I really don't have a good feel. I love to talk more to the microstructural evolution people who might be able to tell us what they think about that. And then I know that Pascal and Carlo have been making new measurements with the LA ICP-MS, detecting impurities at grain boundaries and within grains. I'm really strongly interested in that. Whether that might help us build models to understand what you're asking,